think about how I should deliver the message that I was asked to deliver, which is about compound extremes. Compound extremes usually means that the two extremes of either the same type or different type hitting the same place, knowing that we have a diverse backgrounds here. So hopefully the message will get across. So instead of showing you all these complicated plots, I decided to put the barcode here. So if any one of you very interested in knowing the methodology, you can just scan the barcode and it will take you to the published paper where you can find all the details. Let's first dive into the largest weather system, which is called monsoons, that dictate and modulate our weather. In a mature phase, let's just say around June or July, in the deep of summer, we will have the low-level wind systems, blowing moisture from the southern side of the Indian Ocean to the northern side, right? And then the moisture start to feed into the continent, and then you also got carried through with a little bit, bumpy rides, and then hit Western Pacific, and that's where the two flows of moisture air in the tropics collide, and then they merge. They form and they generate some tropical cyclones along the way, or monsoon trough, and then they start to migrate northward. Okay, so depending on where you are, usually you have precipitation that doesn't simply go up and come down. You usually have cycles like this. So this is from April to the end of October, right? So it's really just a warm season, but you can see that this is the example of southern Japan. The precipitation climatology goes like this. You have an active phase, which is like monsoon, essential monsoon, or in China called Meifang, in Japan called Baoifang, right? And then you have the break, then you have a revival phase. It goes like this. In India, depending on where, you also have similar cycles. Sometimes multiple peaks with intra-seasonal variability. And all this represent circulation patterns that bring you this sudden influx of moisture that later, very soon, right, punctuated by dry period, which will be very hot. That's when the other element I'll be talking about is aerosols. Block sunlight cools the air temperature. So if you only have aerosol, your surface temperature will decrease over time. On the larger scale, it can change the thermal balance or thermal contracts between land and ocean, and then change the larger scale monsoon system. So it has some effects too. So all these different things interplay and then produce all sorts of different and interesting weather phenomena. The first one I want to introduce you to is the summer 2010 Pakistan flood. It's a heavy rainfall event happening in northern Pakistan, but then the flooding covered almost like 1/3 of the country. Very soon after that, we did analysis. Under the framework next, we found out that within this particular event, there are something very interesting. Within about 20 days, northern Pakistan, which is more like a desert landscape, experienced 3 consecutive MCS. If you are a meteorologist, you know MCS, but if you're not, it's called mesoscale convective system, which means gigantic storms that is self-sustaining, and this is way bigger than any of the monsoon rains you are accustomed to. Those are usually found in like the United States, central United States, when you have the specific weather conditions that produce supercells, sustainable storms that move and then produce a lot of rainfall. If you put that rainfall in Nepal during monsoon rain, it may fall into the normal range. But during those times, in that landscape, which is here, it was unusual. So unusual that the river system overloaded. So we call it pre-monsoon storms. What do we mean by pre-monsoon? Pre-monsoon means that before the first wave of monsoon rain starts, what do we experience? High temperature, very hot, right? But also increased humidity, but not so much that it cannot rain every day in the afternoon. So there's a very short period of time, around 2 weeks to 1 month sometimes, that you experience this, we call it conditional instability, which means that in atmosphere, is actually conducive to big storms. You only need a trigger. But usually, around the time of July, the circulation pattern here doesn't provide that kind of trigger. So you're just gonna feel very hot until the monsoon rain comes or it cools down. Just like most of the Indian continent will have experienced during the monsoon season. But during that time, that year in particular, there was an upper level system, the trough, what we call, that dips further south, and they generate a middle latitude type of weather forcing, and then they trigger all these storms. So from satellite, like train observations, we can see those storms, they look like a hook. They form a very sustainable system within the storm. So it lasts a very long time. Okay, instead of raining for 2 hours, it rained for 2 days. We also found that the wave trend has become a more or less a sustaining pattern, like over the period of 20 to 30 years. The wave trend pattern, upper level circulation patterns, start to appear more and more during that time over that area. So not long after, in June 2013, in northern India, observed a similar patterns of a wave trend. Now we cannot read this, but what this paper found was that northern India has experienced increasingly large rainfall in June, because June is the time of the pre-monsoon. So we also are facing the similar conditions, that the atmosphere has become critically unstable. And then the second finding is that we found these amplified short waves that usually was random, but through simulations, through our diagnostic studies, we found that the circulation pattern that leading to these waves, short waves, has become more and more likely. The short waves tend to happen during that time, then provide upper level lift for that. And then, of course, we are very interested in studying Nepal's climate. And presented here are 2 recent studies. And one of them is the recent fire event 2 years back, during one of the worst drought in West Nepal's history, and which led to a series of forest fires that burned around this corridor, and that also caused the air pollution to reach record highs. As far as I know, Kathmandu has his schools closed shut down due to really bad air conditions. And alongside with another study, both of them led by Bino here, reported that even within Nepal, which is a big country, but also not so big, and yet it shows a persistent divide of extreme precipitation climatology over the past 30 to 40 years. If you focus on extreme precipitation events, which also kind of represent moisture pooling or sort of meteorological process, you will see a very clear divide, with the eastern part of Nepal getting wetter and wetter, or more and more extremes. The western part, however, stays about the same, but then in winter season or colder season or dry season, the chance for drought has amplified as well. And that agrees with an earlier research that we did, focusing on Western Nepal's drought. So this was a 2013 paper, I believe, focusing on drought there, because I think it was 2008 at the time. 2008, that Western Nepal underwent its worst drought on record, and that was the 3rd severe drought in a row. Okay? And one thing for sure is that the drought frequency has increased. Intensity has increased too, and it's focused on this area, northern India and western Nepal. And this is an important water resource region. In groundwater, I'm not showing that here, but you can check on that. Groundwater also shows a declining trend, which means the total water storage is not being recharged enough, even through the monsoon season. So it produced some sort of a concern. But as a meteorologist, we try to understand whether or not this is the natural variability or it's something that's amplified by climate change. But we found that the climate change part, the global warming part, was manifest by persistent and strong warming in Indian Ocean, central part of Indian Ocean, that produced this local holiday circulation that with the downward branch roughly around this area, probably explain why Eastern Nepal was spared out of it, because the substance was strongest in this area. And also there's a wave trend coming from a Eurasian continent, which we can trace it back to summertime, North Atlantic oscillation, or sometimes even Arctic oscillation. But those are more of a natural variability that tend to happen in some years. And it happened during 2008, and then coupled with the warming substance that make the drought particularly bad. Next. So I've been mentioning shortwave trends and jet streams. So let's take a look at what do this jet stream really means. Let me try to just verbally walk you through. What's plotted here are winter conditions in the upper troposphere. This is summer part. So let's just look at the winter part. Winter part, you probably all heard about polar vortex or polar jet streams. That's stratospheric jet stream high up. Those have more of an effect on middle latitude countries. But then the subtropical jet is further south. So perturbations on that could have effect on tropical countries or subtropical countries. Now here is the V winds, north-south wind, in terms of climatology. What you are seeing is kind of a wave structure because it depicts northerly wind, southerly wind, and northerly wind, southerly wind. So it's like wave number 3 structure here. So winter time, we have a stronger jet, but longer waves. In summer, it's a little bit different. Summer jet stream is further north. Supposedly, summer jet stream does not affect, latitude north-south to the south of 30 degrees. So Nepal or northern India, Pakistan, supposedly are free of the summertime jet stream. But summertime jet stream has a shorter wavelength. You can see that because the speed is lower, the wave they become more wavy like that, and then it span across Eurasian continent. But with a shorter wave, if you perturb that, the likelihood of it to get deeper will increase as well. Next. And that's what we found to attribute those summertime jet stream. There are many papers that report that the summertime jet stream has become wavier. But they say that in 2 different types, and very few papers to put it together. One of the waviness is stationary. So that is what connects to what I presented earlier, the northern Pakistan case, the northern India case, which means that over time, the likelihood of a trough system happening at that area during that season is increased. That's a stationary wave. The forcing of the stationary wave, surprisingly, does not directly come from like this global warming induced Arctic warming and all those thermodynamic changes. It came from Western Pacific, the warm pool that because it warms up much faster, I should say the heat build up much faster than the rest of the ocean, it constantly generates this Rossby wave energy or energy dispersion that affect the middle latitude jet stream, and they got regenerated over the northern Atlantic Ocean because that's a jet exit area that easily get perturbed, and then it would generate wave trend across, circling back like this from Eurasia continent. So this is the part where, if the condition were right, the wave may penetrate down or further south to affect our monsoon countries. Next. These are the stationary wave dynamics. In a different paper, they also summarized and did some of the analysis to categorize different forcings that will indicate an amplification of the jet stream. But this time, we're talking about transient waves. So they will happen anywhere. What it means, the difference between this and the previous paper's finding is like, this one shows that because, let's just say the summer northern Atlantic oscillation change, or even the summertime Arctic oscillation, what you call NAM is called northern annular mode, second global mode. But this kind of change, or even just the called wave resonance change, just the 2 jets interacting with each other, will amplify waves. But this kind of dynamics happen so randomly you can only summarize. You see the statistics of amplitude increasing. You cannot pinpoint where, because every season, every year is different. So this is a little bit more concerning because it means less of a predictability for that. But still, the dynamics seems to be established. So that's a different paper for that next year. Now let's get down further south and start to talk about the role of aerosols. And this is where I found interesting. So we have done a research that focused on Bay of Bengal tropical cyclones. Think about the tropical cyclone climatology. I don't have the graph, but you can imagine. Now, for instance, think about hurricane seasons, right? And if you project that as a time series, you're gonna see the low storm season and then the hurricane season, right? And then they enter the quiet season again, just one peak. But if you plot tropical cyclone climatology here, it's a bimodal. You have a winter quiet time, and in springtime it comes up, in summertime it goes down, and in the fall it comes up again. So it has two peaks. Particularly in Bay of Bengal, the peak is in May, very distinct peak. Just the May, within these 30 days, magical 30 days, there's a much higher chance for tropical cyclones than any other time. And that made me wonder why. So in May, before the whole monsoon system, circulation system built up, May is the season when this trough here start to deepen very fast, and then get into June or middle of June and integrate with all the monsoon system. But in May, the trough is pretty distinct. In April earlier, there's no trough at all. Sometimes even a ridge. Okay, so this trough is very sensitive to the tropospheric depths. Now, what happened with aerosol, air pollution, that layer of dirty air has built up over time. What happened is it will increase the middle tropospheric temperature. So when it increases, now lower level you see the trough, low pressure. Higher level you actually see a ridge, high pressure. So it means like the middle troposphere is expanding. Then it causes the trough to deepen over time. So is it because of warming? Yes, warming has some effect. As I said earlier, Indian Ocean warming up. So you tend to create low pressure. But also because of aerosol, it's like a double punch effect. Okay? So the deeper the trough is, the more likely you're going to generate cyclones. And not only that, cyclones will become stronger because of warming. And because this trough deepens, cyclones will tend to go to Bangladesh and go to Myanmar more than you hit India. And that has statistical significance trends that we have shown, and they continue to be verified, especially during recent tropical cyclones. Yeah. So it only happens in this very short time of the year. Again, about tropical cyclone in Bay of Bengal. Now, back to 2019, Cyclone Fani at the time broke many records. It was called the worst or most intense tropical cyclone ever recorded from observational records. Okay? And that's when we start to analyze deeper. I just mentioned that overall, the regional aerosol tend to intensify the trough, make cyclones more likely. But if you really simulate the tropical cyclone as we did using WRF model, tuning to the highest resolution to be cloud resolving, and then we turn on and turn off aerosols, and realize that locally within the tropical cyclone, aerosol actually suppress the tropical cyclone a little bit. Next year, 2020, also in May, another cyclone, Amphan, broke whatever record Fani broke. So, but then the big difference during May 2020 is what? COVID shutdown. Without those aerosols, we wonder whether or not Cyclone Amphan was actually fueled or intensified by the lack of aerosol, or translated by COVID shutdown. And we did some simulations, but we didn't really push it to publish that. But this morning, I'm not kidding, this morning I got an email saying our Fani paper was cited by a very recent study published last month by our Indian colleagues, simulating ENFN using MPAS models, and they claim the result that, yes, because if you turn on aerosol, ENFN will have reduced its intensity to like faint or even weaker. So it means that because COVID shut down, clear the air, get rid of aerosols, indirectly make ENFN stronger. So what should we do with that, right? So this is a very complicated environmental issues. All right, so switching gear to the source of aerosols. If you look at the aerosol compound, different season has different compound. Now in wintertime, this is a little bit more serious because wintertime involves a lot of burning. So we have more of a black carbon. And those are more severe because those interact with the solar radiation more. So it will affect our heating. And we have to know that most of the time, the boundary there is shallow. So your air pollution is trapped and close to ground. But not here. Northern India, Nepal, we have very deep aerosol, dirty airs. So that interact with the thermal structure, you make the air more and more stable, and because of that, you trap more air pollutant and make the ground cooler. So you create something like cooler surface, warmer air, warmer middle atmosphere. So you create a virgin. So I want to summarize here why we are seeing compound effects. Now this picture is directly from my condo in Salt Lake City, looking east. There's a wildfire burning. Well, why am I using this for storms? Because the dynamics are all the same, right? All you need is instability, moisture, and lift. Now you can see that here. Yeah, it's clear sky, but you see cloud, so it means moisture is still in the air, just invisible to your eyes. Once you have lift, then you will create condensation. Once you have enough moisture, then you create storms. So all these things will happen anyway if you give it those dynamics. Now, at the larger scale, what we give is through atmospheric waves. That's why in the beginning, I put emphasis on the circulation changes. Now, if you have the wavy system, you will interact with this kind of larger scale lift. So in 2018, southern Japan went through a double punch event, compound event, flood, and then heat wave. So that basically explains what I try to say here. We have the beginning of the summer monsoon, right? And that is actually pushed and also formed by subtropical high, forming those gradients, all those things. We have the monsoon trough here. The monsoon trough keeps supplying moisture, and during 2018, it happened to have a pre-monsoon tropical cyclone, very small typhoons hitting Japan as well. And that all through that, it combined with this wave structure, and then it caused the massive flooding in southern Japan. But the problem is that once the system formed, they keep migrating. They will evolve into the break phase. Now, at that time, still in southern Japan, suddenly the frontal band moved north. What's replaced by that is a subtropical high, very intense one, because the trough was deepened, and then it feeds back like this subsidence motion. Right? And then after that, there's the revival phase. Southern Japan start to get influenced by the monsoon trough. And what's inside the monsoon trough is typhoon. So that year has this typhoon hitting southern Japan as well. So it went through a succession of extreme events. It seems like independent events. But if you look at the framework like that, with the Eastern Asian monsoon system and their evolution, they will go through this cycle, like cycles. Which means within this same framework, your rainy season will get rainier. Your dry season will get drier, which in summertime that means heat wave, because the moisture content is about the same. And then your revival phase, depending on how lucky you are or unlucky, you may get hit by tropical cyclones that, according to observation, have grown over the past 30 years. So this is a summary about what I'm trying to convey here and why, especially in Asia, we can have this compound extreme event. But I believe that if we start to think about a probability of extreme events under a sub-seasonal or seasonal time scale, maybe we can formulate a strategy that can benefit the society. Because of the time range, I won't present what's next, so I will just stop it here. And thank you for your attention.
Okay.